I took all the digits in the MNIST data set. No, in this particular example, I only took all the 4s. I extracted all the 4s, and I built one model for each of the 10 digits. It does work just fine when you have one model for all 10 digits. It just learns to use its latent representation to figure out what digit you're looking at. In this case, I gave it only 2 latent values to work with. How do you know I used 2? Because there's 2 axes here. And I only showed it 4s, and I said, okay, for every 4, tell me what you've got and re-encode it. Well, look at what it decided to use it for. The horizontal axis is very clearly the openness of the top, is it not? Wait.
The size of the bar, the horizontal bar, right? Going up and down.
Oh, it's slantiness. I don't know, it's kind of disk. I have a better one that actually shows what I wanted better. And it's right here. There's another instance of my having done it. In this particular case, notice all the ones on the left have this pointy 4. All the ones on the right have this open 4. And all the ones on the top are just kind of vertical, and all the ones on the bottom seem to be very italicized or slanted. And it'll do it differently every time I run it, but this is one, starting with a particular random seed, the neural network happened to separate out very nicely that one axis is italicizedness and one axis is openness of the top. And that's kind of cool because not only does this understand 4s, it understands different kinds of 4s and can tell me things about them. Things that it decided were important because these are the concepts that vary the most in the MNIST data set. If I were to add another dimension to it, I think it would use that one to indicate boldness. So all the 4s on one end would be not bold, and all the 4s on the other end would be boldified. And of course, the fact that they're nicely separated into axes is totally coincidental. It would probably be some linear rotation that occupies all 3 of the dimensional spaces unless I do something else. Pop quiz, if you wanted to make it so that each dimension represents just one concept, how might you achieve that? Somebody say L1 regularization. Because the point of L1 regularization is it uses as few activating values as possible. Therefore, it will only activate the dimensions that say something it needs to say. So if it needs to say italicized, it'll say that, but it won't unless it needs to. So if you applied a lot of L1 regularization and trained on a big enough data set, and I don't even know if MNIST is big enough for that, then it should start to separate out concepts into different axes, presumably. And in that case, I guess you'd really want to regularize your inputs and not so much the model, because the model needs to do what it needs to do. But your inputs need to specify the type of value going on. Okay. This is very much in the realm of unsupervised learning. Do you see why? Yes?
So when you do it like if you did it on all them nets, you think every time it would take like the most important thing that separates them? So that would be like which digit it is? Or
it's not necessarily most important. It's the one that varies the most in the training data is really what it considers important, because if the error metric is sum squared error, the thing that allows it to minimize sum squared error the most will be whatever varies in the data set. Which I guess, yeah, that's important, isn't it? It's important to it. If you adjust your error metric, you could make something else important. Okay. Now, the big question that comes up in unsupervised learning a lot is So what? I mean, who needs a bunch of 4s sorted by their similarity? Nobody does, right? I mean, this is clearly a toy. This is the kind of thing we do just to prove our algorithm works. So why do we do unsupervised learning at all? Why do we need to reduce dimensionality? Why do we need to understand intrinsic representations of anything? Well, yeah, in this particular case, we're going to be building this recurrent neural net that's going to generate these models of cranes. Let me draw a picture.
You learn the dimensionality of a problem by just trying different dimensions and seeing how much information can still be extracted. If you have some system where you didn't know what the dimensionality was in advance, couldn't you find the dimensionality for this thing and then say, well, now I know, I don't know, that there's like 12 things in the system that are defining or that are...
Yeah, and that's very useful information to have. Okay, actually, let me springboard off of that. Characterize some areas of machine learning. So our data is very often discrete, I'll say categorical or continuous, right? And our operations tend to be supervised or unsupervised. And if we divide up some of the techniques we've learned into these categories, if you're doing supervised learning with categorical labels, so I guess I should indicate that this refers to the labels, and this refers to the approach or method or something like that. If you're doing supervised learning with categorical labels, this is called classification. If you're doing supervised learning with continuous labels, that's called regression. You knew that, right? Okay. If you're doing unsupervised learning with categorical labels, this is usually called clustering. And if you're doing unsupervised learning with continuous variables, it's usually called, we could call it a lot of things. It's usually called dimensionality reduction or manifold learning. And these two terms are kind of used synonymously with each other, but they're sort of different things. The idea of dimensionality reduction is you take some data and you reduce it to as little data as possible that still contains the same information that was in the original data. The idea of manifold learning is assume all your points lie on the surface of some low-dimensional manifold in high-dimensional space. Can we learn to fit that surface? Well, there are several dimensionality reduction techniques that don't involve learning a manifold, but we haven't talked about them much. Point is, the most effective ones and the ones that I'm most interested in right now involve manifold learning, which tends to be a highly effective way of taking continuous surfaces and reducing their dimensionality. Does that make any sense? Okay. So there are a few other things packed into the dimensionality reduction label, which I need to cover, but for right now, these two things are essentially synonymous. All right. Well, having said that, here's the model we're going to build in assignment 6. Sorry about my sloppy writing. And I was going to make a point with this picture, but I've forgotten what it is now. Oh yeah, now I remember what it is. Why are recurrent neural networks hard to train? Because we don't know V. right? We don't know the internal hidden state. That's why we usually unfold them through time and make these great big models, and we have to train them with backpropagation through time. But do you notice how I provided an approach for estimating V right here? We use this expectation maximization approach, where we alternately update the state and the model. In fact, we don't really alternate. We do them at the same time in this case, so it's technically not expectation maximization. But given only observations, we can estimate a low-dimensional representation of them, which I can call state. Look at what that does. If we know state, then how hard is it to train this model? I'm going to claim it's super easy because for right now, let's just pretend we're done with this one because it's totally trained. Now we just got to train this model. Well, do you see how if I just call this one V sub t plus 1, and I just call this V sub t, I could pretend there's no relationship between them at all. Like that, right? Because I know all the V's and I know all of the V sub t's for my entire training data. Do I not? Because, not this picture. Go away, that picture. Because remember, I've got all this training data and I have randomly wandered through all my observations and trained all my state based on it. So after a darn long time, my state has converged to the point where I know the state of every single image in my training data. Therefore, I could very well just forget about those recurrent connections and just use the previous and next states to train this model. And now it's just plain old simple supervised learning. And I can train this thing, and when I'm done, it will be the exact same thing as this model that takes the current state and feeds in the controls and predicts the next state. And therefore, I've reduced the training of a full recurrent neural network into 2 steps. The first step is assuming that we have very high dimensional observations, which isn't always true, so this doesn't work in general, but if you have high dimensional observations, simply using inference to infer the state while training the model will separate this into those 2 components and will give you both the trained observation model and the internal representation of state. Step 2, once you know the internal representation of state, forget about those recurrent connections and just train the transition model using regular supervised learning. And now, voila, we've trained a recurrent neural network, which is otherwise a notoriously difficult thing to do, and now we can celebrate or generate pictures of cranes or whatever it is we want to do with that model. Okay. One of the reasons this is also significant is people are always using LSTM models for recurrent neural networks these days because they're the only ones that work. Well, that's kind of true except for the fact that I got this one working with a regular old style recurrent neural network. So it turns out this technique is not well known and is actually very useful. Okay, so we're going to prove that with assignment 8. You will train your models to, basically I'm giving you this, the picture, not this.
You mean assignment 6?
6, sorry. Did I keep saying 8? In paradigms we're in assignment 8. In this class we're in assignment 6. I got to line them up just so I can think straight. But you'll be picking random pixels, jumping all over the data, telling it what X and Y locations it's at, inferring the state. Once that's done, you'll move on to step 2 and train the transition model. I've said that about 10 times now. I think it's time for me to move on and say, I think you get it. In the end, here's how we're going to test it. Oh, I did have one. I could have been looking at this picture the whole time instead of drawing it over and over. Sorry. I'm going to give you a sequence of actions that is not in the training data. That sequence is really simple. It just moves left 5 times and then goes up 5 times. Well, it actually doesn't move very much because this is frame 5. See, this is frame 0, this will be frame 5, and this will be frame 9. And if your results look like this, you did it right, you know you've achieved full credit. So it's good to know when you've got it right, isn't it? And you could very well feed in more longer sequences that go left, say, 20 times and up 15 times. You can wander through any sequence you want, and it should correctly estimate how the crane moves if you did it correctly. Okay. Few gotchas. When you infer the internal representations of states, sometimes this happens. This is a correct model, but there are a few outliers that just couldn't move into their correct positions. What's going on, do you think?